I'm going to try to make this one, so we have 23 minutes until we're going to have a scheduled break. So try to go through this, you know, in not too much labored detail. The slide deck, however, is long, much longer than it should be for this. And I hate doing this as a presentation where I'm just going to skip through some slides. I was thinking about trying to, redo things. So I was trying to think of redoing some things for just the slides for today. But I wanted to, I think it's a useful slide deck as a reference in the future. So like, all right, well, I'll just keep them. I'll just keep it all together. We'll go through what's important to, as information. And key is not working, so I'll just go with what I had earlier today. So we'll go through this. Like I said, I do kind of hate doing that as a presentation style, but so bear with me a little bit on that. But I do want all these slides out there to go along with, with the conference and with the videos and everything like that. So we all have access to the information later. Okay, so I'm Tom Rondeau. I actually don't think I introduced myself this morning. I introduced myself yesterday, but I forget that they are actually two separate things. So I'm Tom Rondeau. I run the Uniradio project. Going to the architecture, this is architecture of Uniradio is kind of my main job right now. I get to do over-the-air radio on occasion, which is awesome, but mostly I'm dealing with things like thinking about and working with the internal structure of Uniradio. There have been a lot of talks and mention of tags and messages. Now, we decided to do this talk because they are still a little new in the project, but because we started talking about them in just kind of general talks these days, they have been around for a while, so they are getting picked up as just general parts of how you deal with radio systems. But we started with this data streaming model. That's what kind of the radio idea, a lot of FM, AM kind of streaming modems work really well in this data stream context where you just, and this is a kind of photograph that I started with yesterday in my talk yesterday, but all it is just taking a stream of samples, modulating them with some kind of constellation, muxing two different constellations together, going through different things. So data is just streaming through there and just kind of this continuous streaming model. Still a very important model in radio. A lot of the blocks are written around this model. The buffer system that Jonathan went over in his talk a little while ago, all based on the streaming model. But it does have its limitations. And so one of those limitations that a lot of people really kind of get taken back by is this first one here. So it's a directed graph. It's an acyclic directed graph. So there are no loops available. It's not that there's some people think it's just in GRC that you can't have a loop in this data stream. It's a uniradio thing, not just a representational thing. It's a uniradio thing. But as Jonathan mentioned, we try to work on large chunks of data. Data movement is expensive, so you want to do it as rarely as you can, but you want to move as much as you can at one time. So each block in this flow graph is processing thousands of samples at a time. A phase lock loop doesn't work in that context. You need to be a sample away in a phase lock loop or the thing falls apart. It's a very inefficient design. So that's designed into Uniradio that you don't do loops. Now, an individual block, like in fact that clock-sync block, will has a loop inside of it. So there are control loops built into blocks, just not in the flow graph. So it's a limitation, but it's still a limitation for certain things that we might want to do. One of those things is signaling. So there's no way in the data streaming model, unless you try to hack something together, which we've done in the past, where you have like a separate data stream that's like all zeros, and then when an event happens, you say, oh, at this event there's a 1. And so you look at that data stream and you just wait until that 1 flag appears. That was possible for signaling downstream. Not really efficient, not really kind of the natural way that you might want to do something. So that's still a problem. And there's nothing really to help change behavior between blocks. There's no programmatic way for one block, especially a block upstream, right? So again, you can kind of signal with this data streaming model downstream, makes sense. So you might want some other mechanism to do that. But you still do want maybe command and control, right? You want to tune something that's upstream from the block. In my example yesterday, I had this detector. So the detector detected something, and maybe by what it detected is information about how to manipulate that block or that data better. So you actually might want a signal from that block upstream. So that's what we're talking about with the data stream models. So in this case, right, maybe you have detected, like what Ball was showing, where he was using a central stationary analysis to get the sample rate. That might actually be useful. Or maybe, he didn't really go into this, but when he showed you multiplying that signal or raising to the fourth power, you saw these 3 spikes in that. So the 2 edge spikes are proportional to the sample rate, or the symbol rate of that signal. That middle spike, if you're offset in frequency, will be offset from 0. So you might actually use that as kind of a coarse frequency analysis. Okay, I'm 10 kilohertz away from the signal of interest. You might be able to detect that with his detector down below, and then issue a message back to the UHD usurp source to retune. So you're not always doing all that correction in software. You can actually go back in hardware and actually set the tuner. So detect, kind of things like that. There's no way in the data streaming model to have that kind of command and control concept. We also did use this in the ability to, okay, we detected an event that happened, and you want to trigger some follow-on processing. So first detector, or again, like a known word detector. You don't want to process noise, so you can hold it, or do whatever analysis you're doing. But as soon as you see that known word, you can trigger something. You want to be able to trigger it. In this case, though, of course, you want to be able to trigger it sample synchronous. Right? You want that trigger event to be known to a particular sample. So these are the kinds of things that the stream tagging and message passing architecture solve. And then the final thing, the original intent of the message passing architecture was more the control model, to be able to send messages to control things throughout the graph. But it was became very obvious that you could also have chunks of data held within one message and then pass it around. So this burst model, which is what Tim was talking about, showing all those examples of, was the ability to have a packet or a frame. So we just call it protocol. So the protocol data unit, or PDU, is all done through the message passing architecture. So it's the exact same architecture for the command and control kind of concept, but now we're just passing chunks of data as messages. So again, it's like it's a UN vector, a UN8 vector of samples, and then a dictionary to have information about the length of it, or maybe some other metadata about that packet. Let's just go through the tag stream model quickly. Again, I'm going to skip over a few things that are kind of detail-oriented that you might want to know when you're programming the tag stream blocks. But this is just trying to give us some information about what happens. So you have a block, in this case block 0, wants to add some information onto the data stream. So my example, I'll say SNR. Okay, SNR is often useful to do better with your recovery algorithms or your detection algorithms later on if you modify your statistic by the SNR. So say block 0 is an SNR estimator of whatever signal it is. When that SNR maybe changes dramatically, you want to signal that, hey, there's a change in the SNR, and that's going to help understand if we're going to change out the equalizer we use, because now the SNR is too bad for a decision-directed equalizer. So maybe we want to do some kind of a switch like that. So we tag that sample, say, hey, at this sample, we had some event happen, and we're going to pass it down. So that adds a tag to the data stream, or the tag stream, which is sample synchronous with the data stream. So that tag is associated with a sample in the data stream. And then the follow-on blocks get to do whatever they need to with that tag. They can use that, like I said, to update their equalizer, maybe update their caps or their other statistics based on that information. The sync might be one of our plotting syncs, which Tim showed how you can do triggering off of the level, like a normal O-scope trigger, auto or normal. We also can trigger off the tags. So if you can set it, if you know that this tag is a change in frequency, you can set the system to plot whenever it sees that tag. Our metadata files are based on this concept as well, and I'll show that in a second. More detail-oriented slide. programmatically, you just add a tag to the string by using this add item tag concept. And like I said, it kind of logically associates this tag here with a sample in the data stream. So kind of, if you look at this as the sample stream of within the buffer between these two blocks, this block now knows, is attaching this tag to that sample, so down the line, the block 1 can read from that. Now that's what it looks like kind of logically, like we're annotating this sample with this tag. In actuality, we're actually pushing out to a tag queue, and the tag keeps the information about which sample it's affiliated with. So you kind of detail of that. But then on the other side, as I said, the block 1 wants to get that tag, so it's associated with sample, so it says, hey, are there any tags that I might be interested in? And there is, and it's attached to that particular sample. But of course, it's really just popping it off or writing from the queue of tags that it's on its input. So in this case, we use the get tags in range or the get tags in window. Just to explain that concept a little bit more. So this is going to add an item tag. What do I want to really say about this? Yeah, this is trying to explain this concept of how you annotate that tag in time. This is kind of tricky in this case where I go back here, where it's like, okay, that sample, like that's kind of the buffer, but that tag has to be associated with the sample at all time, from the beginning of the flow graph to however many billions of samples you're into the data stream. So that information is kept within the block's buffers. So it actually knows, so there's no longer just this concept of the buffer and what you have in your work function. It's actually going over all time of that data buffer. And so when you're adding your tag, you have to associate it with this absolute value concept. So like here, that this is like looking at the data as just like, again, this infinite buffer in time. So that absolute item number at the very left, that's always 0. So every block knows that the first item it's going to read is going to be the 0th item. And then you just keep counting up. And you count, and to get that information, you ask the block, on my input buffer 0, how many items have I read from the beginning of time till now? So I know that in my window, within my blocks, in the work function, when you're looking at the window of samples that you have this n items read here. So up to here, we know exactly how many we've ever seen. In our window, we have from basically our relative item value number from 0 to, I'm just kind of using a sync block concept here. So we have those n output items, so that's how many items we're told that our work function has. So relatively speaking, we're from 0 to n output items minus 1. But absolute time is going to be this relative value plus the n items read. Again, kind of use this as kind of a crib for when you're dealing with stuff in your own work block. Getting the tags. There's two concepts for how you get tags. So the work function needs to know, hey, did my SNR change dramatically? Do I have to do anything different in my work function? So let me see if there are any tags here. So it's going to say, okay, within this range of samples that I'm interested in, are there any tags that are going to affect my processing decisions? So there's two ways to do that. Get tags in range. The range version uses the absolute offset, so you have to worry about this n items written concept and try to modify your thinking from what's in your work function to this infinite buffer in history. The more clever one to use is the get tags in window, and that's actually going to be the relative offset. So you can just say, my window, I only know that I can look at my data stream from 0 to n output items minus 1, so I can give that as my window, and the iterating is to translate that into this absolute time offset. And that's probably a really confusing concept when dealing with these tags. Again, that's why I kind of have these slides in detail here, so we can go back and reference it when we need to. There is a concept also of when you, I often introduce this stuff thinking about a block that has one input and one output. So it's easy to think about how tags move, right? This block is going to generate tags, this one's going to receive it, it's going to pass it on. So tags follow the data down the stream. But what happens when you have multiple inputs and multiple outputs to a block? we have a propagation policy that we define for the tag region. So in this case, the all-to-all is the default, and so any tag that comes in input port 0 goes to all of the output ports. Saying anything from input port 1 goes to all output ports. Because you just want to make sure everybody downstream gets the tags that you created. So that's the default behavior. The only other behavior that we really define is the one-to-one. And so this has to have an equal number of inputs as outputs. And so just so anything that comes in input 0 only goes out of output port 0. Only a few cases where we've actually employed this one, but it is available. Finally, there's a tag propagation policy don't. So stop passing tags. We're actually going to kill them right here. We're never going to let them move forward. This is useful if you need to do some, if you're doing a lot of weird manipulation of the data stream, because you want to make sure that your tag is associated with a particular item. But that item no longer exists in the data stream. Maybe you want to drop that tag, or maybe you need to move that tag elsewhere. So you can do whatever you want with the tags. So you want to work with the tags yourself to move them. But if you don't move them yourself, with this policy, the scheduler will just stop it. So nothing downstream will see your tags. So those are different ways that you can move them within your block. Then there is this concept of, again, the sample rate, or the sample synchronous concept of the tag is attached to an item. What happens when you go through a block that says rate changes? Something that upsamples or downsamples. You need to move that tag associated with whatever change is happening. So there's this relative rate concept. So decimator, you decimate by a factor of 10. So you're going to take 100 samples in, you're going to produce only 10 samples out. Where do those tags go in there? That's defined by this relative rate to update those tags. So we handle the tag propagation through rate changes automatically within the scheduler. The tags are also useful, as I said, so you can see them in the Qt time sync, Qt GUI time sync. There's also the Metafile Sync. So we talk about data files for storing data and recovering data. The Metafile Sync was designed kind of with a little more of a scientific method in mind, where you might want to have annotation on your data. So there's now a header within this data file that identifies the time of so think about, okay, the segment is going to be some number of, by default, 1 million samples long. So that first sample is going to be, the header kind of identifies the information on that first sample. So the time that sample occurred, what was the receive frequency, what was the sample rate of the data stream at that time. All that is put into a header that we then can read out the data and keep track of things that change. So if we're scanning frequencies, every time we change frequencies, we can start a new metafile header to keep track of that. And all that's handled by the tag stream. All that information is in the tag stream. So here's an example of, we've already seen this, I think, if you can see that at all. The tag is associated with just event. And this event is where I just took that userv and I changed its frequency. And I triggered off of that, off of the RX3 tag. And then I delayed the trigger a little bit so we can see the event happen. And you can see the transients of the receiver when we change that sample, when we change the frequency, you see the transients of what occurs in hardware with that change. The metadata is, we can actually pull that out. We can read the metadata information from a file. So you get all this information about about what the segment contains, how many bytes are in the segment, and how many sample items, because we know that there are floats. So this is bytes, the number of bytes in that. So it's a complex float value with a particular time. So this is actually the GPS time that I've extracted from the UHD devices. That's a time, that's a tag that comes from UHD. So all that stuff gets kind of automatically dumped into the data file for us to use. Okay. Messages, I think we actually probably got a pretty good idea of what messages are for from Tim's talk. There is this PubSub, so a block will publish a message, and anybody that is subscribed to that port will receive those messages. And then, we'll talk about the thread safety issue here either, because Jonathan already explained that in the scheduler, how inherently the handling is thread safe, because the the scheduler of each block is doing the handle messages and then the work function. So there's no overlap in the thread safety concepts here, which is pretty nice. What's this called? Text all dial. Yeah, so you can publish, okay, tags, I forgot to mention this, tags are almost all, actually generally always handled in the work function. Because they're sample synchronous, there's no point, there's no real information how you actually associate samples to tags without being inside the work function. Messages generally are published in the work function, but they don't have to be. You can actually publish them elsewhere. Let's skip a little bit of this. Just know that there is this connect concept. So when Tim showed you connecting the data strings, and then you had the message connection. So in GRC, we saw those dashed lines to the gray ports. That's a message connect. Very much like the top block connect function, which does the data stream, this is the message connect. And so we're connecting, this block is going to publish under this port name, and and then another block is going to subscribe to its own port, which is going to handle that message input. So this is kind of what it looks like in, I think, a quick example where I'm just going to look at the frequency response of data that we're sourcing from a user, a UHD block. And you can see that I've done these connections so that you can turn on message ports in these a lot of the Qt GUI syncs. So this one, every time you double click on the display itself, on the frequency display, it actually emits a message. And whoever's listening to that message can use that information to do something. So in this case, what I've actually done is it's a loopback. I've actually connected the output frequency to the input port, so I can actually issue messages to that says, hey, retune your frequency. So I can actually tell this thing to retune itself, and I'm telling the user upstream to retune its frequency. And that's one of the nice things about the UHD model is that it does have this command message control thing. So here I'm looking at our favorite signal, Verizon's LTE downlink. It gets me data wherever I am in the country, basically. Those 10 megahertz are really important right now for data movement in the US. So up there at 751 megahertz, I see something, but I've mistuned my receiver, so all I've done, I'm not going to do this live, but all I've done is I can essentially see that little spike there, and just put the mouse over there, double click, and it recenters. It actually tells the user, hey, recenter at 751, and adjusts everything, so the flow graph responds to that back there. This is in the manual, so don't worry about parsing this. This is in the manual, but I just wanted to explain that there's a huge amount of stuff that you can do with the UHD system through this message passing concept. So you give it a key value. So the key in this case was frequency or freq, and the value was some floating point value to telephone frequency of 751 megahertz. But then there's all the PDU-based stuff as well. In this case, we have, so we've talked about this in the past year, is the FEC API. So here's a FEC async decoder, right? So we've already moved into this PDU concept. So we have a bursty message that's a packet with a payload that's encoded with LDPC, and you want to extract that. So we're using a PDU concept here to move into the PDU model, get the payload, do the LDPC decoding, defined up here by this variable block, with some gameless file definition, does the LDPC decoding, now passes on that message that's the plain text. It's going to pass that along to a CRC block. So that CRC block was written to check look at the data, calculate the CRC, check the last 4 bytes of the payload, make sure they match. If it matches, if the CRC is correct, it will output a message that we can pass to the network stack. So now we have an IP frame coming out. So let's say this is our MAC frame. Identify that it's correct, pass it on. If the CRC check fails, no PDU is published. So we can do a lot of stuff with the PDU model. Yeah, this I'm going to fix this slide. So I'm working on this slide. There's a lot of message passing stuff out there. Tim has done most of it, so that was starting to get a list of stuff, especially what Tim has done. But you saw a lot of that just previously. I'll end on this. This is kind of Jonathan had his own version of this, but this is kind of my version of the kind of that scheduler of a thread, that thread per block. So every iteration we come in, so you're posting messages into that message queue. The first thing that the work function or the thread, this run one iteration, this thread scheduler does, check if we have any messages. If we do, let's call a message handler for that particular message. If not, let's call it to the work function if we have data. That work function is going to operate off of the data stream. Any tags are in the input buffer, and then it's going to produce data on the output stream and move tags or add tags or do whatever it needs to do with tags on the output buffer as well. So that wraps up the very quick overview of dealing with message passing and tags. We're just 2 minutes over time, but any quick questions that I can possibly address right now? I think it's pretty dense, but hopefully at least gives you a little clue as to where to look when we're dealing with these things and what they're useful for. Oh yeah.
So with the messages, like on the sort of PubSub, how does it handle like network dropout? So like if you have a laptop that's monitoring something on the network drops out.
All right. So the question was about network dropping. So somebody published your. I think there's maybe confusion over the message passing is all within a shared memory model. It's actually not going over a network stack or anything at all. Yeah, it's all kind of part of the kind of shared memory of the radio flow graph. We do have control over networks. That's what this control port that Jonathan kind of mentioned a little bit. That would happen, and then that's a separate topic to discuss. We talk more about control port. But yeah, message passing we don't have that issue. So you're just posting one block or the same shared memory system. So you're just posting it to directly to the message queue of the block that we know about in this flow graph. All right. Yes.
Is there something fundamental in new radio that prevents adding cycles?
Yes, so as Jonathan mentioned, in the work function, we're trying to work with as many samples as possible, and it's dynamic. So at one point, your block may be working off of 5,000 samples. The next time around, maybe it's only working off of 55 samples. How do you manage a loop of samples when you don't know how many samples away you are? What's the kind of methodology that you want to think about? What's the kind of map that you want to do when you don't know how far away you are in time from one call port to the other? But that's solving. So we solved that with the message passing because you don't want to do math operations like that sample time specific. That doesn't make sense when you're dealing with thousands of samples off. But as I said before, you can do that within a block just fine. We have things like loops as a block. And so you can do loops all you want inside of that work function of the block, and that's pretty easy, just not in the program. All right, I'm going to wrap that up, so thank you.